Hi, it's Mr. T here, and today I'm going to go over the Doppler effect. We're going to look at some problems that might arise from the Doppler effect and how we might use some calculations to solve these. So before we get started, let's just go over sound waves and how they propagate. So in this slide here, we can see I've drawn a picture of a car. That's this wee red rectangle here. And the car will produce a sound. Let's say that someone is holding the horn down on the car and it's producing a sound, and each one of these circles represents a wavefront, or the peak of a sound wave. So this is the peak of a sound wave, this is the peak of the sound wave here, 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 and here. And the distance between the peaks is defined as the wavelength. Now, if the car is stationary, if the velocity of the sound, which is Vs, equals 0, sorry, not the sound, the velocity of the source, the object that is making the sound, if its velocity is 0, it's going to produce this uniform circular pattern of wavefronts. And what the wavefronts are doing is they are moving out in this direction away from the source. And they move at a speed, a constant speed, and their speed that they move at is called VW. And if this is air, it's 343 meters per second. Now, we also have, if we have a wavelength and we have a speed of the wave going through that wavelength, then we also have a frequency, how many times that wavefront will, say, go past the observer per second. Now, the frequency that the sound is produced at the car is called F, and the frequency of the sound that is observed is called F dash. If the car or the sound source is stationary, the frequency that is produced equals the frequency observed. F equals F dash. Okay, so what if the source is moving? So if we have a car, just like this one here, that is producing a frequency F and is moving at a velocity Vs. This is what we're looking at. It also, remember, produces a sound wave that moves at this speed, Vw. Now, the sound wave moves, if we're looking at the direction of the sound wave towards the observer, because this is what we're interested in, the source or the car is catching up with the previous sound wave that it's produced. So if it was still, if it was staying still, there would be a regular distance between the sound waves. But if it's going in towards the observer, it's catching up with the waves in that direction. So we say that the wavelength is decreased. The observer sees a decreased wavelength. If the observer sees a decreased wavelength, then, and the velocity of the wave stays constant, as we've talked about, we can use this equation here that the frequency equals the velocity over the wavelength. So this is the wave equation. Now, if we know that the velocity stays constant, this one here, we can produce a proportionality statement. That is, that the frequency is proportional to the wavelength. So in this case, we've said that the wavelength is smaller to the observer. See, the waves have been squashed up as they go towards the observer. So therefore, the frequency that the observer is going to hear is larger or higher frequency. So as a source moves towards an observer, the wavelengths get smaller because the wavefronts get squashed up. And because the wavelengths are smaller and wavelength is inversely proportional to frequency, the frequency heard is higher. And you know that because when you hear a car coming towards you, you can hear a sound like "nee." And then when it goes away from you, you hear the sound like "no." So as it goes past, you hear this sort of "meow." You hear this change in frequency. The high frequency as it comes towards you, because the waves are getting squashed up, the wavefronts, the wavelengths made smaller, inversely proportional to frequency, so you hear a higher frequency. Well, what if it's going away? If the car is moving away, then you now have the wave, the velocity of the wave is going in one direction and the velocity of the source is going in the other. So the source is moving further away from the wavefront, and now we get a longer wavelength. Because we get the longer wavelength, remember the wavelength is inversely proportional to the frequency, we are going to hear that lower frequency, that right, the lower frequency as a car is receding away from you. So here's a type of exercise that we might have to solve. So here is a car and it's moving towards the observer. We have a frequency of 160 hertz, possibly from the horn of the car. We have a velocity of 27 meters per second. So the car is, if you multiply that by 3.6, you can work out how many kilometers per hour it's going. Somewhere about maybe 106, 110. And we know we've got the velocity of the wave or the velocity of sound traveling through air, which is 343. So we want to, what is the frequency that is observed by the observer at this point here? This is our observer, just standing there in front of the car. Hopefully when the car gets towards the observer, it will swerve and not hit them. So there are two equations that we use to solve this type of problem, and often they're put together as one, but I've just put in each version here. There's if they're moving closer or going towards, we have this equation here, and if we're moving away, we get this equation. Obviously, in this case, the source is going towards the observer. Now, just be careful here. It's that these two are moving closer together. It does not have to be the source going towards the observer. The source could be standing still, but if the observer is going towards the source, they will still hear that higher pitched sound, and they will still compress up the wave fronts and produce shorter wavelengths. So what frequency does the observer hear? Well, we take this moving closer equation and we substitute in the values, we substitute in the frequency, the speed of the wave in the medium, and the speed of the source. And then we get an answer of 173 hertz, which is higher than the emitted frequency. And remember, that's what we expect, because when something comes towards us, we hear a higher pitched sound or a higher frequency. So what we can also do is we can use the same equation and we can calculate the velocity of the source if we know the two frequency. If we know the frequency the horn produces and we can detect the frequency that we hear, we also know the speed of sound, we can work out how fast it is going. So this is, we're going to use this equation here now. So this is, it has an addition on the bottom instead of subtraction. I mean the velocity of the wave source plus the velocity of the wave in the medium. So what we're going to do now is I'm going to rearrange this equation into a form so we can just plug in numbers and solve it. What you could do instead is put the numbers into this equation now and simplify and then solve, but let's just do a wee bit of algebra here. So I want to make a Vs the subject of the equation. I want to put this on one side by itself. And in order to do that, I'm going to have to do some rearranging and some simplifying. So first step, let's move the frequency over to the other side. So it's multiplying on the right at the moment. So I take it to the other side and divide it. Then let's move the Vs to the left-hand side. So it is now not on the bottom. It's no longer a denominator. It's on the top of the equation. So we move this across and we get this here. So we've moved this from the bottom here and we put it on the top of the other side. Yep. So now we need to expand this term. So we expand and we get this. Now this is getting quite complicated now. So what I want to do is I want to get rid of the coefficients in front of the VW and the VS. And in order to get rid of those, the easiest way is to divide all terms by f dash over f. So here we go. Now when I divide all terms by f dash over f, I get VW plus VS equals VW over f dash over f. Now if you know what happens when you divide fractions, you can actually multiply by the inverse of the fraction. So VW over VS equals VW multiplied by the inverse of this fraction, f over f dash. So we get this. And now all we need to do is move the VW to the other side, and boom, that's our rearranged equation. Substitute in the values, and we work out the speed of the sound source, 29 meters per second. Well, let's look at another example. So this one here is a boat, and it's traveling towards the observer. In this case, we don't know how fast the waves are traveling in the sea. The boat, as it rocks up and down, is producing waves. It's moving at a frequency of 0.85 hertz, but the observer notices a frequency of 1 hertz. The velocity of the boat is 8 meters per second. So if we take all of those three, we want to find out what VW is. Now these two are moving towards, the source is moving towards the observer. So we're going to use the equation of VW minus VS. So again, I start to simplify like I did in my last problem. And then we get our, once we've simplified, we get this equation here, VW minus VS equals V dash over, V over V dash times VW. I want to get the VWs on the same side, the terms with VW. So I move them to the other side. So I basically, what I did is I moved this over to this side and made addition. And then I multiplied everything by -1. So the addition became the subtraction, and in front of here became positive again. Now this is still got 2 VWs in there, and I need to get it down to 1. So what I need to do is to factorize this. Oh, sorry, not factorize, the reverse of factorizing. So we take the VW out, and I get VW equals 1 times f over f dash. Now you see here that this equals VW times 1, and this equals VW times f over e dash. And now all I need to do is rearrange this, and VW equals fs 1 over f dash. This is my rearranged equation. Now, this is quite involved steps here, quite complicated. You need to make sure you don't make any mistakes. Again, you could substitute in the numbers for a start and try and see if you could work it out that way. It's usually easier, but if you are confident with your algebra, you can rearrange it in this form. So the boat's producing the wave frequency of 1 hertz. What is the speed of the boat? So we take this equation, we substitute in the values, and we get a speed of 53 meters per second. So these are the types of questions or problems that we get when we are looking at an object that is producing a sound and is moving towards or away from an observer at a constant speed. There are also other situations when the object is accelerating towards the observer or away from the observer. And my next video is going to look at that. Okay, thanks for listening. If you find this helpful, subscribe and you'll be notified when I put other videos up.